mean, for me it's a special pleasure since I have been participating to one of these, I think one of the earliest schools on this, was it the first one?
2000 is the one.
I mean the one with the cat?
No,
2004.
2004.
Okay, so, and it was really a great experience, and I hope it's going as well for you here. And so the lecture will be about dynamics in strongly correlated quantum gases, and I will split between, use mainly the blackboard and a little bit slides. And what I hope to give you, I will not be able to give you an overview about all the dynamics done in ultra-cold gases because this is just a very, very tight field. But what I hope to give you is to give you at least an insight into some of the experiments which can be done and discuss them a little bit so that you can know yourself what is reasonable, what can one do, what can one design, as well to make proposals what you want to do. And so I have seen yesterday that Eric gave already a very nice introduction, and I suppose Dan as well, to the ultra-cold gases. And so I will keep relatively brief on this introduction, but nevertheless I would like to repeat some of the main points so that the notation is clear and you are following, even if you haven't seen the lectures before. So it will be mainly the dynamics in strongly correlated systems. And Eric gave you already a nice introduction how to grade these degenerate gases in experimentally, or what are the what do we call a quantum degenerate, when do we reach it? And I would just like to give a very brief introduction into this. But let me first mention the main, so I will give an introduction, mainly in this first lecture, and then I would like to focus on two systems later on, and one is a two-terminal setup in which transport has been seen. And so I will mention very different experiments, but I will concentrate on describing you one of the experiments more in detail, which is an experiment by Tilman Esslinger's group at the ATH in Zurich, which had been designed by Henning Moritz, who is now in Hamburg. And so it looks a little bit like this. You have two reservoirs. Which are connected by a channel. And so typically what they have at the moment are lithium atoms in this system. And I will describe you a little bit what has been done. So this experiment is relatively recent, 1 or 2 years old. I will describe you a little bit what they have done in this setup and what is possible in this setup in future or relatively easily. And the next systems I would like to focus on are lattice systems. And there I'm not yet fully decided what kind of dynamic situations I will present to you, because there is such a wide class of experimental situations that it's very difficult to pick them. And I will see, in particular, depending on the time, what to focus on and on your interests a little bit to discuss it. So let me say for the introduction, I would like to recommend some books. So it's first of all the Atomic Physics book of Foote. Then it's Patting and Smith. I think it's called VC. And Stringari. And Pitaevsky. And for strongly correlated systems, there's a recent a review by Emmanuel Bloch, Jean Dalibard, and Willi-Zerga. Which is very extensive on these strongly correlated systems. Okay, you have seen yesterday, that to reach the quantum regime, what is important is that in these gases, that you have now not gases which can be considered as point-like anymore, but that the Debye wavelength of these gases becomes of the mean distance between the particles. Let me try to sketch it over there. And so what this means is that what you need is that the density times the Debye wavelength becomes of the order of 1. And so just to give you a feeling of the different systems, let me give you some examples of the degenerate temperatures and as well the energy scales which are relevant in these systems. And so I will take a nuclear matter electron gas like in solids and an atomic gas. Certainly these are just orders of magnitude which I give you. So the density will be measured this is the degeneracy temperature, and let me give you as well a time scale, at least a rough time scale for some of these systems. So here in nuclear matter we are really, really dense. Whereas if you look at the electron gas, it's 10 to the 23. And the atomic gas is really dilute because otherwise it would solidify. And so we need to avoid to be too dense in this system. So it's really several orders of magnitude difference in between these systems. And this leads to a different degeneracy temperature if you measure in Kelvin or electron volt. I don't know what are your favorite units. Yes?
Sorry, by degeneracy temperature, do you just mean like Fermi energy?
So degeneracy temperature, sorry, I should have said this. So what I take is just that somehow this product, which depends on the temperature, is approximately 1.
So it is Fermi.
Sir?
It is Fermi.
Which corresponds in most systems to Fermi temperature. But for bosons, it's the boson temperature. And so if you look in Kelvin, it's about 10 to the 3 for the electron gas, whereas it is about 100 nanokelvin in these atomic gases. So it's really, really small. These gases are at very, very cold temperatures, but one has always to take into account, compared to the energy scales, they are hot. So please be aware of these. The absolute temperature is very, very cold, but this doesn't mean that in the systems you are really, really cold, because for example, these fermionic gases, what you are typically at is 0.1 T/T². So it's compared to condensed matter systems, it's hot. It's really, really hot. And so just let me give you, if you think in electron volt, the corresponding values, whereas I will mainly think in Kelvin or Hertz, so I will use these kind of scales. So why can we now do so well the dynamics in these cold gases? This has as well to do with these energy scales. Because what you see is that from these energy scales, which are very, very small, you get very long time scales. So to measure the dynamics will be quite easy. So where we are in fermionic systems talking about picoseconds or femtoseconds, what we are talking in these cold gases is milliseconds or seconds. And so you see, for experimentalists, to tune a laser in a few seconds or milliseconds, it's easy. In condensed matter physics, to do something on picoseconds or femtoseconds, it's much more difficult and demanding. So this is one of the big advantages of the cold gases in order to look at dynamics in these systems. So these atoms, so what I discussed here mainly is the external motion of the atoms. So the atoms don't have only an external motion, but they certainly have as well an internal structure, which we typically neglect if we are talking about the dynamics or their experiment in these cold atoms. But I mean, experimentally, be aware that this internal structure is really, really useful, for example, to manipulate these systems. And I will come back to this a little bit later to show you how to trap these atoms or how to prepare different states in these systems. In particular, one typically uses different internal states for the spin states of the systems. And one uses these as well, for example, to get the atoms so cold. One uses laser cooling, evaporative cooling, which all rely on using the internal structure to manipulate the atoms to get these to these cold temperatures. But I will not give you the details on this cooling. So this is very well described in these books. So if you are interested, just go to them and read them. Yesterday, Eric told you a lot about the scattering of the atoms. Therefore, I have shortened this introduction on the scattering very much, but I would like to repeat just the main points to make clear what kind of notation I use. It will be very similar to the previous notations. So, as Eric mentioned, what we have, the scattering between these neutral atoms is now not the Coulomb force as you are used by charged particles, but it is the van der Waals potential. And this van der Waals potential has a tail which goes like 1 over r to the 6, with the average distance or the separation of the atoms. And this is very, very different from the, for example, the Coulomb potential, which goes like 1 over r, because this potential can be considered as short range. What does this mean is that at low energies you can really approximate this potential, everything until 1 over r to the 4, you can approximate by a delta potential. And as Eric said yesterday, so what you have in this potential is you have about a few hundred bound states in the potential, and you are dealing now with a state which is coming in around 0 energy. So this step is about 1 electron volt. So now, if you look at the scattering state, typically in quantum mechanics, what you do is to write it as an incoming wave function, an incoming plane wave, which is then scattered, let's say, at a spherical potential. So what happens is that you get a scattering amplitude, which typically depends on the momentum, only the absolute value of the momentum, and you get a spherical one. And so, typically we are not interested in the detailed structure of this scattering, but what we are interested in is only the low energy properties of the system. Since we are relatively cool in temperature, only these matter in most of the experiments. Not all of them, but I will just talk about experiments where these matter. So at low energy, for the potentials we are discussing here, what one can define is the scattering length, and it's defined as the limit of the amplitude for k goes to 0. And so this scattering length, Eric said it yesterday, can be tuned in these cold atomic gases from attractive to repulsive, and you can tune it over several orders of magnitude using a resonance which is called the Feshbach resonance. And let me just give you one very nice review on the scattering. Beside the books, which I have already mentioned, there's a nice review on the magnetic Feshbach resonance. By Köhler et al., which is there you find a lot of details of this system. And so let me summarize a little bit what we have up to now. So we have now atoms which are quantum degenerate and can move around, so they have a kinetic energy, and they have this scattering potential, which we can now approximate by a pseudo-potential, which has the same scattering length. And so the pseudo-potential, which is typically chosen, is just the delta potential, and so typically one takes 2 times delta of r, but please be aware in 3 dimensions this is not well defined, and typically what you would need to do is to take the pseudo potential, which is defined by the delta potential, times this expression, which means that you apply this now onto the wave function. So I will always just discuss this one, which stands in short for being, for considering this potential. And so there is a very nice exercise in the book of Jean Dalibard and Badebon, which I would recommend everybody to do. So there's as well an English version. It's just the basic quantum mechanics book. And in the chapter on scattering, theory, you calculate a little bit the scattering states and the scattering length for this kind of potential, and showing that you need to take this term into account if you go into a three-dimensional system. Okay.
So is that
Yes.
psi of r is the scattering state?
Yes.
The,
So it's
so
the wave function, or is the operator of the particle.
so the state comes into potential energy?
No.
Okay.
It's
Let
a
me-
Schrödinger equation.
It's the it's the term in the Schrödinger equation.
Oh,
So typically you have the Hamiltonian applied to your wave function, so it's understood to be this wave function. Over.
But the point is the derivative acts on psi as well.
Sorry?
You need the derivative acts on psi as well. The derivative?
The derivative acts on psi, exactly. And this is why I write it like this. So the derivative acts on r times psi. This is why I don't just leave it out, because then you can misunderstand it. Yes?
What happens if we don't use this?
You don't find the correct scattering angle. So you don't have a potential which has the same properties as the potential you want to have.
I see.
In 1D, it works totally fine. So there it's totally valid just to take the delta function. But if you do it in 3D, you don't find the same scattering. Leo?
Well, just maybe helpful to say that in 3 dimensions, delta function doesn't scatter.
Exactly.
If you really take a limit of zero range and infinite strength, the way you define delta function, you'll have no scattering. Just because if you have a hard disk, if you have a hard disk repulsion, a hard sphere repulsion, then the scattering length is set by the radius of the disk.
I see.
But so that if you take the disk to zero, you have no scattering. Only in 3 dimensions, but 2 dimensions, 1.
Exactly.
So this is a way to regularize that.
Well, maybe instead of a zero width, you can also choose a finite width to represent.
Yes, certainly. I mean, you can choose different potentials which have the same scattering length. This is just a typical one which is often chosen. I mean, exactly what Leo said is done in this exercise. You see that if you take the delta function, you don't find the scattering if you don't regularize it. So, I really recommend if you're interested to do this exercise. Okay, so now the scattering length which one gets out is related to this amplitude g, which is just proportional. And it has just the prefactor of the scattering. So you see, you can really tune, by tuning the scattering length, you can tune the amplitude of the interaction in your Hamiltonian. Okay, so maybe to summarize this, I would like to write down the Hamiltonian, which we now have for many body systems. So the description of the external motion including the scattering can now be written as a many-body Hamiltonian where you have your kinetic energy. So psi is now the creation operator of your boson or fermion, depending on what kind of system you have. And I take here now the sloppy writing of the delta function. So I just take the states at the same place, which couples suddenly to the density square in our situation. So additional to these two terms, what you can have is as well potential, which acts on the system. So let me write this down, which couples to the density of the system. And so this is now somehow the starting point of the many-body Hamiltonian, where you have kinetic energy, the interaction energy, and the potential term. And so I have written it in this form just for one species. What you can certainly do is if you have more species, you get a spin dependence in, you might get different scattering depending on the spin. If you take different atom species, you do get different masses in here. So you have a lot of variety how to play with these systems and get different Hamiltonians from this. But this is one of the basic many-body Hamiltonians which you get out. Are there questions? If not, I would like now to put a little bit of focus what you can do with this potential and tell you a little bit on how to shape optical potentials for these ultra-cold atoms. And I take optical potentials because this is one of the most flexible ways. I mean, typically in experiment you can as well assume magnetic potentials. But I think if you understand what you can do with the optics, you have already a lot which you can play with. To do this, I will describe a little bit the effect of atom-light interaction in the very simplified way of having just to consider the internal states of the atom as a two-level system. So this is certainly a harsh simplification. But I mean, to get in more states is typically easy, and you understand very well how it's done if you understand this situation well. So this is now the internal states of the atom, so the ground state and the excited state of the electron. And let's say that the atomic resonance is given by omega 0. So the Hamiltonian of just this two-level system would be diagonal in these eigenstates, and you just get this is now a single particle Hamiltonian of just these two states with the energies. So now what we do is to shine in laser light. And we will treat it classically. This means this is only valid if you shine in really, you absorb many photons during this process. So then we can just take a field to describe the light, which is given by some amplitude with a certain direction where I have the polarization in, and I get the oscillating part with the light frequency, and the propagation, which I directly neglect, because typically the wavelength of this light field is about several hundred nanometer to be close to these resonances, and the size of the atom is a few angstrom, so we just neglect this dependence for the moment. So since so this now couples via the induced dipole interaction to the atoms. So this means that the interaction term in the Hamiltonian couples to the dipole operator of the atom times the light field. And the dipole operator, we just take now one electron, which we consider is proportional to the position of the electron in the system. And so what we get out, if we consider the matrix elements, what one sees by symmetry, if one considers the symmetries correctly, is that the induced dipole moment can only be there if you do a transition between G and E. So you get only outer diagonal elements for this coupling. And so your Hamiltonian, you don't see very well if I write down there.
Sorry, before you erase that, I want to ask you a question about the pseudopotential. So when you write down the Hamiltonian, so do you use the pseudopotential you just wrote there, or just use G delta R?
Exactly. What I used here was just this delta interaction. You see that these wave functions are all taken at the same place, which comes because I consider the delta interaction.
Yeah, but
so I don't take the pseudopotential term here into account.
But you just said, the pseudopotential. I mean, the G delta R is ill-defined in 3D, and I mean, what we usually do is to introduce a finite width, and that introduce a cutoff of the momentum. But so
this is why I said when I wrote this, be aware. What I mean by this is this pseudopotential. I just write it as the delta potential here, since I will mainly deal with, this is the way people typically write it in a sloppy way, but one has always to be aware that one either needs to take a finite extension or do this if one deals with three-dimensional scattering.
Okay. You mean what really people mean is to write down the full, to use a full pseudopotential you just wrote, right?
Yes.
Okay.
But Gross-Pitayevsky equation will be obtained only from this form when we assume it local, yeah?
Okay. We will come back to this.
It depends when you want to get out. So like if you just not really calculating with it or doing mean field theory, then it doesn't matter. Then it doesn't matter to put that detailed form of it.
Yes.
But when you actually want to connect G to the scattering,
then you need to take it into account. Okay, yes.
Sorry, just a comment about this issue. So in principle, you can keep it as a real delta function as long as you have some UV cutoff, right? And in the end, you take some limit of this G going to infinity in the right way with the cutoff also going to infinity to keep the scattering length fine.
Yes, there are many, many cases where you don't need, to take this potential in your many body calculations, because you put it in either by doing mean fields, you don't need it. If you put in the correct kind of cutoff, you don't need it. So, I mean, there are many ways to get around this potential, but if you want really to connect it back, typically you should not forget that this is the scattering which you have to take, connect it back to the original scattering. And this is why I write it here with a warning, because this is a mistake which is easily done. Okay. Then let me come to the now single particle Hamiltonian of just this two-level atom. So the Hamiltonian is now a combination of the atomic Hamiltonian and the interaction Hamiltonian, which is just given by the atomic levels, where I have now put the zero of the energy in between the two levels, and the off-diagonal term which comes from the coupling to the light field. You first of all have this oscillating amplitude, and you have an amplitude to it, which is called the Rabi frequency. And so this is the matrix element and so what is quite important to see is that you can tune the amplitude of, or the Rabi frequency, by just tuning the intensity of the light field. So this will be later quite important. So this Hamiltonian is just a 2x2 matrix, which is now time dependent. And so let me just, so this you can solve yourself as an exercise numerically or analytically. And so let me just discuss two situations. Here, since I have written down this Hamiltonian, let me discuss the case where we are close to resonance, which means that the light frequency is close to the frequency of the atomic levels. And so what one will assume here is that typically the distance, or the detuning, how it's called, the distance between omega 0 and omega L, is much smaller than omega 0 and omega L. The second situation I will consider, which is the important situation now for our potential, is that we are far off resonance. Which means that this detuning is much bigger than omega 0 or omega. So for the first situation, this is important for state preparation. What I will show you by this is that you can now prepare, by using a light pulse which is close to resonance, you can prepare your state either in the ground state, the excited state, or by some superposition of it. And this is important for example, if you want to do spin flips, or if you want to prepare your state in an entangled state between two spin states, or things like this. So let us look at the probability to find find our atom in the excited state. And so we assume that initially we prepared it in the ground state. And so what you do to do these calculations, which is easy as an exercise, you can go to the rotating frame of the atom. So what you do is to scale out the rotations which are just due to the atomic Hamiltonian, and then you neglect fast rotations which is called the rotating wave approximation. In order to find the solution of this situation. And so the solution is given by an expression which has a prefactor which depends mainly on the Rabi frequency and the detuning, and a time-dependent factor which is just a sine squared function which depends on time. And the frequency is now given again by the Rabi frequency and the detuning. Of the system. And so what you see in this expression is that you can now really, let us first discuss the case where we are really on resonance. So this is 0, this factor is 1. So we get really here the Rabi frequency as the frequency of the oscillations, and one finds that if one considers the time evolution of the probability to find the state E, one has just oscillations which go up to the amplitude 1. So this means now that here you absorb photons to get to the excited state. Here you are totally in the excited state. You, after this you have an emission of photons, you go back to the ground state. And so in between you create entangled states of the ground state and the excited state. So this is how spin flips or these manipulations in these systems can be made. So what people say to prepare, for example, the excited state, they make these pipe pulses, which is going until here, that you really switch all your atoms, for example, in the excited state in the system. And so, for example, by this you can imagine making a non-equilibrium situation where you have, for example, the spin up prepared everywhere, and then suddenly make a spin flip in part of the system, for example, a localized region, or you make half of the system, or some other combinations. Yes?
So in experiments, this Rabi frequency, what's the typical value?
The Rabi frequency really depends very much on what you try to do, because I mean the Rabi frequency is the amplitude of the light field. So what I mean, it depends what kind of states you have over here, for example. What kind of frequencies you need. So the laser frequencies are more the important part. For example, if you just want to drive transitions between different hyperfine states, which are very close in energy, which are typically split by gigahertz, you use radio frequency pulses. Whereas if you have here transitions, like it is often done between S and P, internal states of the atom. So this can be of the order of, 10 to the 14 hertz, so it's 700 nanometers or something like this. So just to give you the rough idea, it depends very much what are the internal states used and the intensity
So
of
you
the
just want to
laser.
have like a feeling like, is it too hard to do this preparation very precisely? You have to time the time that you shine the laser
Yes,
for.
okay, so for example, if you use here S&P states, the laser light, the frequency which you need to be on resonance is about 700 nanometer, for many of the order of 700 nanometer, which means it's about 10 to the 14 hertz. So it's very, very fast compared to the external motion of the atoms. So typically you can take this internal states flip as something which is instantaneous compared to the motion of the atoms. So let's say this time here is really, really fast. It's about 10 to the minus 14 seconds, if you have there hertz or a factor of this, but of the same order, compared to the milliseconds or which you have for the motion of the atoms. We just so I write typically compared to external motion. Yes?
I'm not sure. Are we confusing the resonance frequency and the Rabi frequency a little bit? So the resonance frequency is sort of, just the resonance of my laser, but the Rabi frequency can be totally different. It has nothing to do with the resonance frequency. And that oscillation, the Rabi oscillations are controlled by the Rabi frequency, not the laser-like frequency.
Yes, but typically, the time scales which are, okay, so the laser frequency you need for this is of this order. And what you can make is, the Rabi frequency depends totally on the E0.
Yeah.
This is somehow, you can tune from 0 to something. So this is why I cannot really give you an order of magnitude there. It is of the order of a few hundred of these time scales typically, but it depends very much on the transitions which you are driving. Is it a radio frequency transition? Is it a transition between S and P? Is it a different transition? But typical time scales of these pi pulse, it's much faster than the time scales which are in this situation, or the external motion of the atoms.
Yes. You can guess, I guess you can make the preparation as precise as you want by making the electric field then arbitrarily small in terms of the time, right? Because what determines how you prepare the initial states or how long you shine the laser, right?
So typically the resolution of the state preparation depends on the length of the pulse. So there you need to take care that you don't do, what we assumed here is really somehow a cosine light field, but this is not what you do. You typically do a pulse of this light field. So what you do is not exactly what I have said here, but the Rabi frequency is now the integral over the changing Rabi frequency in the pulse, and therefore you can, engineer it quite a bit. But what is quite important if you have proposals, just go and see what kind of atom do you want to use, what kind of states are you talking about, and look at the scales which you get out. With this you can get a rough estimate, even though I haven't shown you how to do it for the pulse, how to do it for many levels in the internal structure, but it gives you at least a rough order of magnitude of the time scales. Now there are more questions. And let me just mention that, this typically you can do as well locally to the system by shifting the resonance. For example, by shifting these energy levels over space, that they are only on resonance at a certain position in space. And so this is very easily done. Or they can do it nowadays in experiments very accurately to really just address a very, very sharp region of your system. So what I have not said here, which I now assume by saying this, is that if you go off resonance, what happens is that this amplitude decays quite rapidly. So you see here, this detuning comes in, and the frequency becomes higher of the oscillations. So what happens is, if you go away of the resonant case, is that you get now, let me make a new plot. Oscillations, the amplitude of which is far from being 1. So this is really quickly decaying in space, or in resolution. Okay. So this is somehow to give you a handle on if you want to do something on different spin states, if you want to prepare in time rapidly situations which are locally or some other switching of the spin states. Now let us go in the situation of this far off resonant case. I have already mentioned here that you will not see these Rabi oscillations anymore because the amplitude goes down considerably. And so we are now taking ourselves in the case where this amplitude is really, really small, and I will tell you what happens in this situation. So this is often as well called the light shift, or the AC Stark shift. So what one can do in this situation is not to go in the rotating frame of the atoms, but of the light field. And so what one finds then is that one gets an effective Hamiltonian, which is now of the following form, where you have the detuning delta on the diagonal and the Rabi frequency on the off diagonal. Yes?
Sorry, just to be clear, this formula here, is it general or meant only for small detuning?
No. This is general if you're close to resonance.
Yeah.
So this is in contrast to what typically Cummings meta theorists do, just perturbation theory, linear response. This is an exact solution, exact in the case that one has done a rotating wave approximation, which means one has neglected frequencies which are of the order of omega 0 plus omega L, so really quickly rotate. And so now we can calculate these new eigenstates of this Hamiltonian. And since we are in the rotating frame of the light field, what I do is just to look after a period of this rotation. So I look stroboscopically, and I do directly approximation, which is not necessary, but makes the formulas easier to write, which is Faraday tuning. And so, I mean, you can just take this Hamiltonian and diagonalize it, and then connect back with the rotating frequency of the laser light to the original states. And what one sees is that these new eigenstates, which one gets, is now connected to the old eigenstates of the atom, which were at omega 0 half, minus omega 0 half, and omega 0 half. And you get now a correction to this, which I just write in second order in the omega squared over delta. And in the other way, it's the other minus sign. So what this means is that you now shift your levels which were at minus omega half and omega half. And what you do now is that if you switch on this Rabi frequency from 0 to a finite value, you shift your energy levels by this correction. So this is now, for example, shifting up. If I take, now I need to take care. So if I take the delta, which is this expression, to be smaller than 0, this is shifting up. And it's shifting down here. And so you see, you can now do the shifting of these energy levels depends strongly on the Rabi frequency. And further, the sign of it does depend on the detuning. So if you change the sign of the detuning, you change the sign of the shifting of these levels. Yes?
Can you say, so in the first analysis, near resonance, you ignored the fast rotating compared to detuning. You ignore the high frequencies, which is the double.
Yes.
Yes.
So what you do
Transition
here?
frequency compared to the tuning. What are you ignoring here? When you write down that Hamiltonian.
If I write down this Hamiltonian, let me see.
Seems like it's the same Hamiltonian.
Yes, it is. I think, but this I will look up, I will tell you next time, just not to say something stupid here, is I think you neglect the omega 0 plus omega L, which is much bigger than the difference in this case, but I will look this up and tell you next time.
I mean, the Hamiltonian looks the same.
The Hamiltonian, first of all, looks the same, exactly. What you do now is a little bit different, so you look really at, what you did to get there is that you go to the rotating frame of the light field, so that you have now additional oscillations with the light field on top of this, and you look at fixed, let's say, periods to get the steady state of this situation. So what you have, if you would look at real-time evolution, you would have some oscillations on top of it. But I will tell you next time what is going inside. It's two-line calculation to get here, and so on, to do it. And so this condition, which I have written down here, is not necessary. So you can have as well bigger Rabi frequencies. If you do the diagonalization of this Hamiltonian exactly, you get just the square root expression here, which I have expanded in the big Rabi frequency over the dTu. Okay, what does this mean now? Why do I say this is fantastic to shaping potentials? What this means now is that if you have this kind of shift, which depends now on the light field, what you can do is to take a light field which is spatially dependent. And what this means is that this shift will depend on the position in space. And so this is exactly what you need for creating a conservative potential. So let me try to plot it an example.
Sorry, in the Hamiltonian, should the delta be actually omega 0, or, I mean, that's Hamiltonian. I mean,
Sorry, again?
the Hamiltonian is written as h bar, h equals h bar over 2.
This is the Hamiltonian.
Yeah.
After you have performed the rotation of the light field. So you have taken your state. So your state I represent as a vector as C, G, and CE. And so what I do now is to rotate. I do a transformation where I go to mu, which I rotate by omega L half, I think, and the other in the other field. And then you get this Hamiltonian. And this is very important because this Hamiltonian has not the oscillating factor anymore. It's really a static Hamiltonian. So you have created an effective Hamiltonian which is now static and describes the situation, but only, I mean, neglecting these fast oscillations. Yes?
Shifting the energy levels, can one think of it as a renormalization of the gap or the distance between the state and the...
Yes, it is, exactly.
And then it depends on the strength of the interaction between the atomic field and the other.
Yes. And in particular, I mean, it depends on this, like we said, the interaction, the Rabi frequency was proportional to the amplitude of the light field. And so this is the important thing now, which we will use. I mean, the induced dipole element you cannot tune over space, but this is what you can tune over space.
Sorry, but if so the condition is the delta is much larger than the omega, the Rabi frequency, right? So if I look at the Hamiltonian and I just do perturbation theory, so the zero order is just the delta and the minus delta, right? So, but you have h bar omega 0 instead of, you know.
Yes, so I left out one step, which is going back to the original basis. So I think I will just give you the calculation, a copy of this, that you can have a look at it. I didn't want to spend the time to do the calculation here, but it's really easy, and I recommend everybody who has to do with this to do it once in your life. I mean, it's I'm now doing it typically in quantum mechanics course. And so what you're seeing here, you diagonalize this Hamiltonian, but you need to take into account that you have done this shift. So your energy levels will be shifted back by this frequency, sorry, some might not see it, omega L over half. And if you combine this correctly, this delta gives you this omega L over half, cancels this, and gives the omega 0 over half, which is here. There. Okay, so what we have seen is that the light shift, the light field causes a shift of the energy levels. And so what this means is that what you get is an induced, or this gives a conservative potential. Which is typically called the induced dipole potential. And so this potential is now a potential which is typically written in a slightly different form than we found it over there, which is that you take a prefactor, which is the polarizability. So here you see it's proportional to omega squared, which means it's proportional to the amplitude square, which is just the intensity of the light field. And so this is here the intensity of the light field, which we have here. And so what you have done, or what we have done here, is now to define everything else on the details of the atoms, on the detuning into this alpha. But I mean, it's good to remember that it's proportional to 1 over the detuning, such that you can change the sign and that you can make it different for different spin states in the systems. But really, I mean, use the numbers. So this is called the polarizability of the atoms. And typically you can find this value, for different spin states, besides the detuning, which is going like 1 over the detuning.
Excuse me.
Yes.
In the dipole approximation, I thought you ignored spatial variations.
So
you put
up to now, I ignored spatial variations. And now I'm putting them in back by hand.
Okay.
So that we have the spatial variation of this light field. But what we take only into account is that the intensity varies very slowly compared to the atom size, so that our calculations are still correct on the microscopic level, and we have just that this light field is now changing in space. So let us do an example. And we take for this just a focused ready-tuned laser beam. So ready-tuned means, you are at the long wavelength. This means that delta is smaller than 0. And the other case is bluely tuned. If you're at short wavelength, the delta is bigger than 0. And so if you now plot the intensity of the light field versus space, let's take just one direction, what we get is just typically a Gaussian envelope for this kind of beam. So let me plot just something like this. So what does this now mean for the atom levels? I should have used a new blackboard. Always. Can you see down there, or should I? Yeah. So let me replot this here. This is the intensity. So this means now that the EG level, so we have chosen delta is equal to 0, smaller than 0, so it's the same case as here. So we see if the intensity goes up, the level goes down. So we get for the level something like this. Whereas for the excited state, we get something like this. So you see what now happens is that these ground state atoms, or the atoms which are in the ground state, are attracted to the intensity maxima of the laser beam. Whereas the atoms atoms which are in the excited state are repelled. More precise, in G state, are attracted to the intensity maximum. And this is how you create a dipole trap. You take several laser beams, you focus them such that you get a potential which is now attracting the atoms to a certain position in space. And typically what one does is that this kind of focusing potential, the Gaussian envelope of the laser beam is relatively big to the size of the cloud. And so what you can do is to approximate this by a parabolic potential, which is the typical parabolic potential considered in this description of cold atomic clouds.
So this is reticule or woodicule?
This is reticule. So this was reticule. For plutitune, it's exactly the counter. Plutitune, you have the trapping in the minima of the laser beam for the ground state, and you have the trapping in the maxima for the excited state. You just change the sign.
Excuse me.
Yes?
Is it like two types of atoms on like some sort of superlattice? Because you have one type in the ground state, which is at one particular position in space, and the other type is in excited state and in a different position in space.
Yeah, so we are not yet in lattices. So this is just a dipole trap. So what happens if you do this preparation is that the ground state is just trapped and the others escape. They are gone. If you go into lattices, you can play with this and you can make this combination that one atom sees somehow the maxima as the minima and of the intensity and otherwise. So there is a lot, what you need to do for this, for example, is to use atomic species. Typically what one does is to use two spin states, for example, down here. You use a transition which is going in between of them. So it is reticune for one of them and plutitune for the other. And then you have the situation which you mean that if you have an optical lattice potential, one of them is attracted, so one of them sees this kind of potential, whereas the other one now sees as the inverse of this potential. So this is really a possibility to play a lot with these kind of situations. So I first wanted to summarize now this and then say a word of warning on this kind of situation, since it's not as simple as that in all cases. So by shaping the intensity many different geometries are possible. We can certainly tune the intensity relatively rapidly and as well change the geometries rapidly, because this is just the changing of the laser intensity. So this is very nice if one likes dynamics. And can be different for different spin states. or atoms. I mean, certainly the detuning or the internal frequency which we consider depends on the atom you take. But just a word of warning, put really numbers in before you say it's all possible. I mean, there are limitations to it as well. So let me just try to put numbers. And one of the points which one needs to take into account is, here we talked about far detuning. If you now want to create situations like this, you might be not as far as you want to be. What does this mean is, what I have totally neglected in this situation is spontaneous emission events. And so this I have just totally neglected here. But what you can have is somehow virtual excitation or excitations to the state, and then spontaneous emission events which let your atoms decay to something else. And so what happens then, or heat up the atoms, and so these kind of events typically scale like 1 over delta square. So if you are getting too close to the resonance, or if you are not far enough of resonance anymore, you need to take these effects into account. And therefore, typically people say that in spin-dependent lattices, if you think of something like this, you have more heating effects, because you have these spontaneous emission events which you need to take into account. But, I mean, one can get around this by using different types of atoms or engineer their ability.
Sorry.
Yes?
These spontaneous emission events, how should I think about it? So the levels you derived are sort of eigenstates of the laser, or of the...
Combined system, yes.
Yeah, but they're not eigenstates of something else, right? And so what is it that they're not eigenstates of that can occasionally introduce transitions from S to P?
So what you do have is a coupling of these excited states to the vacuum field. So what you can have is here an event where if you have an excited atom, it will decay after some time without any laser influence by coupling to the vacuum down into the ground state.
So you're really treating the field classically. There's no photons or not. You treated the electromagnetic field classically.
Yes.
So there's an n+1.
But you have as well, I mean, if you don't apply an external field, you have this decay.
Sure.
So this was,
So that's the +1.
and so this decay I have totally neglected, and this is what needs to be taken into account.
I see. So it really is just coupling with the vacuum. I see. And so can I think that the rate of this spontaneous emission is related to the intensity of my admixture between S and P states? Or the intensity wrong, or the more mixed the S and P states are, the bigger the rate of spontaneous emission. So is that right?
What do you mean exactly by mixed?
To find
typically, different levels have different decay rates because of symmetry, because of the coupling. Yes. Let's discuss this after.
But if you think of your basic Hamiltonian, you have atom that's coupled, minimally coupled to vector potential. So even in a vacuum, it's not just a single particle problem. It's not just the atom problem. It's coupled to the quantum fluctuating vector potential. Yeah, that's the thing that.
And the coupling does depend on the level which you consider. And in general, the picture I presented was just two states here. Certainly this is a very simplified picture. You have many of these states. You typically need to take an average of these many states into account to get the correct description.
More generally, you can just think of it as it's a many-party problem. You have photons and you have an atom. So it's not a Right.
Yes, so what Leo said is just to describe this spontaneous emission already without the laser field. What you need to take into account is, I mean, for example, the easiest to see this is to take a box, take the vacuum modes of the photons which are possible into account, and solve the now many-body Hamiltonian of a single atom with this coupled to these photons into account. Yes?
I think maybe, if I'm not mistaken, what the intuition Brian is asking for, maybe correct me if I'm wrong, is just a statement of how in the Fardy-Tune limit, there's basically population in the excited state. If you think about there being population at 1 over delta squared or omega squared over delta squared. So then the decay rate is exactly related to that population. It's gamma times omega squared over delta squared. That's right.
Okay. Yes, I mean, it certainly depends on the detuning because you have a certain probability to excite the state, but it's as well the coupling to the vacuum. Okay, so I will need these potentials very much in the following to shape different experiments. And in particular, we will as well consider an optical lattice potential later on, which is just formed by standing wave light fields where you have a periodicity in the system. But I mean, knowing now how to construct this, you can construct really different geometries, but take always, I mean, by just calculating what kind of, this intensity of the light fields can be. So you need really, if you want to see what kind of lattice structures is possible, or what kind of geometries are possible, what you need to calculate is this amplitude, which is typically giving, if you have different light fields, you can take the sum of the amplitudes and then the intensity of it. It's a trivial statement, but I mean, you get the interference terms, which can play a big role and can give you really nice effects in the system. Okay. So are there further questions to this? So we know now how to create our atoms in certain states. We know how to create different confining potentials, change them in time and space. And I mean, then we can do it relatively quickly. And so, as said, we erased the many-body Hamiltonian. So if we are now again interested in our many-body problem of the external motion, we have our many-body Hamiltonian. We can have different spin states, different atoms, which I just label by the spins. And I write down the same form of the Hamiltonian which I had before. And so here now the interaction can be in between a spin species or different spin species. Let me just, write this like this. So you have to take a little bit of care what you have there. If you have fermions, bosons, depending, you will have different terms there. And you have the potential which can as well depend on the different spin species in case you want. And so now for the dynamics, we have many knobs. I mean, we have first of all the interaction strength. This is typically tuned by the magnetic field, and so there you need to take care that the timescales you consider are on the timescales which the experimentalists can really stabilize the magnetic field rank. So typically this is not as instantaneous as the other things. Let me just note that the interaction strength can as well be tuned by tuning the confining potential. For example, if you take, if you confine your atoms much more inside a potential, the effective scattering will go up because the overlap of the wave functions is much stronger, and you can change by this as well the interaction strength. Then you have the tunable geometries. And this can be made almost instantaneous. But you can certainly as well do something slow here. There you have a wide range to play with. You can do lattices, disorder, 1D, 2D, 3D. Really a lot of different geometries. Then you have the internal structure. This was now the preparation of the spin states, which we have seen on resonance, which you can tune as well, almost instantaneous. Let me write very fast. In these systems, and you can do it locally or globally. But be aware, if you use different spin states, be aware of how they scatter with each other and what kind of Feshbach resonances do exist, and really look at the species which you want to consider to see if the situations you want to design are possible. So by using this kind of internal structure, you can as well kick the atoms, give a momentum kick, or do something like this. So let me write down here. So first of all, spin states. But as well, you can do momentum changes. So, for example, excite your atoms in these systems. Okay. So this is somehow the many-body Hamiltonian which we will deal with. And let me just say, so I have not discussed any external coupling here. So certainly in realistic systems, there is a little bit of heating. And depending where you are, there are particle losses. But on typical scales of the experiment, you can find situations where you have an almost isolated system and can really study the almost isolated dynamics in these systems. So relatively well decoupled. Most heating effects are spontaneous emission. Or let me say, incoherent light scattering. Or if you are close to Feshbach resonance, resonances where you have really strong interaction, it's as well the particle losses which you need to take into account. And I think Eric will talk more about this in his lecture. But this good decoupling from the environment means as well that in contrast to solid state systems, you cannot think of the atoms as being at a certain temperature. You don't have a thermal bath. Or you can think of them at a certain temperature, but if you do changes to the system, like a change of the geometry or things like this, you do change the temperature of the system. And so in many situations, it's better to think of entropy in these systems. Because in the case that you can do very, very slow changes, you can be approximately adiabatic. Certainly you are never really adiabatic in experiments, and conserve the entropy while doing a change to the system. So be aware of this. There's no thermal bath which gives you the temperature of the system. Okay, and so I see I haven't gotten as far as I wanted, but it was very good that there were so many questions. And so next time I would like to talk about transport in these systems and give you a little bit of first an overview of different experiments which have been done, and then discuss the experiment of Tiltman Esslinger in more detail. With the knowledge we now have, you should be able to understand very well what they are doing. And then in the last lecture, I would like to come to lattice setups and try to tell you a little bit about the dynamics there, what one can do in these systems. Over.